Hello, hello students. So now let us look into another topic called as bias and belief network. So right, Navy bias classifier we have seen. So how we are going to how we use the bias theorem and try to classify by using the probabilities. Now there one important assumption what we have made is that conditionally independent, that means all attribute values are conditionally independent to the target value. That was our main assumption. Now why the concept of bias in belief network comes into the picture, let us try to understand here. So now the Navy bias classifier now assumes that the Navy bias classifier assumes that all variables are conditionally independent, right, given the value of a target variable. What is your input variables? These input variables are attributes. These are conditionally independent to our target variable. That was the assumption what we have made in our Navy bias classifier. Now in our belief network, Bayesian belief, now you just look into the term belief. So you are going to believe. Now these belief network allows stating conditional independency assumption that applies to a subset of variables. Now the basic concept is very simple here, try to understand. Now we might be having some training example wherein which some subset of variables out of so many attributes values, some variables, some attribute values may be conditionally independent. Now whereas some variables may be dependent on some other variables, right? Or say for example, now you might be having some values or the attributes to identify the probability of that attribute, to calculate the probability of that attribute, right? It is very difficult, you don't know how to calculate it, you cannot calculate itself. Now at that time you can derive that value from the other values. You can derive, like say for example, now you want force is equal to mass into velocity. Now this is the simple equation in physics in your elementary school. Now you are in such a situation where directly you cannot calculate the force. Since you cannot calculate the force, now this force is dependent on some other values, mass into velocity. If you know the mass, if you know the velocity, then you can try to calculate the force. That is what this says. So in some of the examples, some attribute values may be independent, some attribute value may be dependent on some other value. So in that cases, now we try to use the bias and belief network. So it is an intermediate approach that is less constraining than the global assumption of conditional independent made by the Navy bias classifier. So globally, the main assumption in our Navy bias classifier is that all are conditionally independent, right, but more trackable than avoiding conditionally independency assumption altogether. See, what happens is that you cannot completely say that every time all the variables are independent, all the attribute values are independent. So certain times there might be some variables, some attribute values which are conditionally dependent. Now in that cases, now we go with this Bayesian belief network. So in general, a Bayesian belief network, it describes the probability distribution over a set of variables. So here we are going to look into a probability distribution. So now this probability distribution over set of variables. So this distribution generally it is called as joint probability distribution. Now consider an arbitrary set of random variables. Now you consider some variables y1, y2, etc. up to yn, and these are random variables, right? These are random variables. You don't know, each time it might take some values. So where each yi can take one set of possible values. So v of yi, some set of random variables we are having. Now we define the joint space of set of variables y. So joint space means you know that sometimes the y may be yes or sometimes y may be no, right? You have to consider everything. So you are going to consider set of joint space of the set of variables y to be the cross product. How? So v of y1 into v of y2 into v of y3, etc. we are going to take the cross product, and the probability distribution over this joint space, that means when you considering everything or this space, is called a joint probability distribution. And this joint probability distribution specifies the probability of each of possible variables, each variable y1, y2, etc., binding our tuple, right? Now this is how what we are going to consider. Now let us go into still more deeper. So let us try to understand what is mean by conditionally independence. Now let us understand the idea of conditionally independence properly. Now we say that x is conditionally independent of y, right? X, listen carefully, we say that x is conditionally independent of y given z, right? X is conditionally independent of y given z if the probability distribution governing x is independent of the value y given a value for z. It is little bit confusing, right? Now let us see here. Now what we are saying, for all xi, yj, zk. So we have some random variables, right? For all x, y and z. Now we are going to say probability of x is equal to small xi. You take any instance, right? Probability of x is conditionally, like this we are going to write, probability of x is conditionally independent of y comma given z. Probability, we say that x is conditionally independent of y. How we are going to write x? We say x is conditionally independent of y comma z, given z, given z, right? If the probability equal to, if the probability distribution of x is independent of value y given a value for z. So then we now you see here, then we are going to remove this y because x is conditionally independent of y, right? So we are going to say equal to probability of x is equal to xi for given z, right? So where this small xi, yj and zk belongs to that random variable. So here we have said, right? So all this random variable y, x, y, z, now three are we are taking, right? So where each variable yi can take a set of possible values, v of xi, v of yi and z. Now we commonly write this above expression as follows. So we are going to say probability of x given y means x is conditionally independent of y given z. So then we can write it as probability of x given for this variable z. This is how we are going to write the conditional independency. Now the definition of conditional independency can be extended to set of variables also. Now we can extend that to set of variables, not for one, we can extend it to more number of variables. Then we can say that set of variables x1 to xl is conditionally independent. Now you can see probability of x1 to xl is conditionally independent given in y1 to ym, independent, conditionally independent of set of variable y1 to ym, given set of variables z1 to zn, comma z1 to zn can be written as probability of x1 to xl given this z1 to zn. Now there is, now we say that a relation between this definition and our conditional independency definition in Navy Bayes classifier. So in Navy Bayes we told conditionally independence. Now this, now we are trying to associate with that. Now how we are going to do it? Now the Navy Bayes classifiers assumes that the instance attribute a1, right? You are having one attribute a1 is conditionally independent of instance attribute a2, right? We are saying attribute 1 conditionally independent of attribute 2 given for this target value v, yes or no, play tennis, yes or not going play tennis. Now there how we write in our Navy bias classifier, probability of A1 comma A2 given V. So A1 is conditionally independent of A2 given this target value V. So now we are saying VNB equal to argmax of, this is the standard equation of our Navy bias classifier. Now we try to modify this. Now we say that probability of A1 comma A2 given target value V equal to probability of, see, A1 is conditionally independent of A2, right? Now we say probability of A1 given A2 comma V, right, comma V multiplied with probability of A2 given V, right, probability of A2 given V. So which is equal to probability of A1 given V multiplied with probability of A2 given V. It is nothing but, it is a product, right? It is a product of a probability of A given B, conditional, how we are going to say probability of A given probability of B, and probability of B equal to probability of A into probability of B, the basic probability rules. With that rules we are going to say now, when you say probability of A independent of instance A2 given a target value V, then we can write it as probability of A1 for the target value multiplied with probability of A2 for the target value, because both are independent. Since it is independent, you can find a product of both the things, right? Now let us go into the representation. So now when you look into the representation here, a Bayesian belief network, right, now it is represented by joint probability distribution. So we are going to use a joint probability distribution, and also we can see that there is no, when you try to draw or when you try to look it as a graph, it is acyclic graph. It is a acyclic graph. Now let us take an example of this. Now here is one example is there. Now we have got storm, we have got bus tour group, you have got an attribute lightning or a variable lightning, you have got campfire, you have got thunder, you have got forest fire. Now when you try to look into these things, right, so now the Bayesian network is a diagram, or it is a pictorial representation of the joint probability distribution. So joint probability distribution over the Boolean variables. Now here we are taking some variables. What are that? Storm, lightning, thunder, forest fire, campfire, and bus tour group, right? Now these are the variables. Now what it is telling is that when there is a storm and a group of people who goes on a tour, right, now they at night time they make a campfire, right? If they make a campfire, there is a chances that because of that small campfire there can be a fire in the entire forest. That is one case. Another case, there might be a storm, because of storm lightning comes, and if there is a lightning and because of that lightning there is a chance that there can be a fire in the forest, right? Now assume that you have got a scenario where there is a fire is caught in a forest. On what basis there is a fire in the forest? Now as far as this particular diagram, now there are two possibilities where the fire can exist in a forest. One is because of storm. So there was a storm, there was a lightning, and because of that lightning forest fire occurred in a forest. Or there is another thing, some people went to a forest, they made a campfire in the night. Because of that campfire some incident happened, that because of that there is a fire in the forest. Now you see that this is the variables, and with a pictorial representation now we are trying to draw this. And a Bayesian network represents the joint probability distribution by specifying a set of conditionally independent assumptions represented by a directed acyclic graph. Now there are certain independent assumptions together with set of local conditional probability. We have got both independent assumptions and there are certain local conditional probability. Now you go to this diagram. Now if you look campfire, the campfire is it an independent or dependent? Now you can see that campfire is dependent on storm and bus tour group, right? It is dependent on these two. When you take thunder, thunder is dependent on lightning. Now what about this forest fire? Does the forest fire depends on the thunder? No. That means these two are independent, conditionally independent, right? Whereas this lightning, campfire, storm are dependent for this forest fire. If you want to identify forest fire, so there are three things: either because of lightning a fire can occur in a forest, or because of campfire a fire can occur in a forest, or because of storm also fire can occur. Now what is the probability? What is the chances? So now this becomes conditionally probability, which is dependent. So some probabilities we can see here. So a Bayesian network represents the joint probability distribution by specifying a set of conditionally independent assumptions together with a set of some local conditional probability, right? So each variable in joint space is represented by a node. So we are going to represent each of these variables as a node in our diagram, right? Now for each variable, two type of informations are being specified here. Always when you're talking about a variables, now there are two types of values are being specified. What is the first one? The network arc represent the assertion that the variable is conditionally independent of its non-descendant in the network, given its immediate predecessor in the network, right? So when you are drawing, so first one thing is that the arcs, their arcs represent the assertion that variable is conditionally independent. The second one is a conditional probability table. So one is given, one we are having the arcs, these arcs, right, which gives us how it is dependent and how it is independent. The second one is that we are having one table. So a table is been given for us. What is that particular table? It is a conditional probability table. We call it as conditional probability table, and it is given for each variable. For each variable, describing the probability distribution for that variable given the value of its immediate predecessor, right? In this table, now you can see this is the table. This table is for only campfire. It is for this campfire. You can have a table for lightning. You will be having a table for thunder. You will be having a table for forest fire. Like this, you will be having a table, different table. These tables are been given, which talks about the conditional probability of his immediate predecessor. In this example, the table is given only for one variable, campfire, right? So now the joint probability for any desired assignment of values, right, of our network variable y1 to yn can be calculated. It can be calculated by the formula. What is that formula? How do you calculate the joint probability? Probability of y1 to yn is equal to product of, for I equal to 1 to m, probability of for each variable vi given its parent value, right? Because it is very clear, if I want to find probability of this, I should know its parents, based on its parent from storm and from bus tour group. So this is how we are going to calculate the joint probabilities, right? Now this Bayesian network, as we are telling, it represents the joint probability distribution. The same thing is been given here. So now we will try to see what is this particular table, this right side of our table. Now how that table you are going to read. So the left side entry in the table, for example, express the assertion that probability of campfire equal to true. Probability of campfire equal to true when storm is equal to true and bus tour group equal to true is equal to 0.4. What is this? I think it is very clear here. Now you see here, so this campfire is represented as C, right? Let me take the cursor. Okay, now this campfire variable is just represented as C. Now there, right? Now forest fire, it depends on all this storm, lightning. Right now we are just looking into this campfire. You forget this now. Just look into this variable campfire. Right now, what are the possibilities? Either you can have a campfire or there is no campfire. Negation means there is no campfire. You have not put any campfire in the forest, right? The two things can happen, right? Now when you consider this campfire C, now it has two parents, storm and bus group. Now let the storm be represented as variable S and bus tour group, let it be represented as B. So now S, B. Now S comma B. Now when you take the first variable 0.4, now what it says, the probability, right? See here, probability of campfire equal to true. Probability of, this is only C is there, campfire equal to true. What about this now, negation C? Probability of campfire equal to false. But now probability of campfire equal to true. This first row is all true, campfire equal to true. Second row is for all probability of campfire equal to false, right? Now when you take this campfire equal to true, the first value 0.4 is what? This is the conditional probability when we are saying storm equal to true and bus tour equal to true. See, both are S comma B. S means what? Storm, which is equal to true. B is bus tour group, which is equal to true. So the probability is 0.4. It is given for us. Now you take second variable, right? S comma, what is this? S comma negation B. Negation B means what? Now probability of storm equal to true and probability of this one bus tour group equal to no, false. That is why negation B. Third one is negation S. Storm is no or storm is false, bus tour is true. And the fourth case is storm is also false and bus tour also false. This is how you are supposed to understand. It's very simple. Try to understand. So this table provides only the conditional probability of campfire given its parent variable storm and bus tour. Like this, you will be given a table for lightning, you will be given a table for thunder, you will be given a table for forest fire. Clear? So like this, the tables are being given for us. Now what actually we are inferring by this probability of Bayesian belief network? Now here we might wish to use Bayesian belief network to infer the values of some target variable. So this target variable forest fire, you don't know how to calculate the forest fire, as we told. You don't, sometimes it is very difficult for us to calculate the force, right? So but we know force is nothing but mass into velocity. Now we have a means through which you can calculate mass, you can calculate velocity, but you don't have, assume that you don't know how to calculate force directly. At that time it is being derived, force can be derived by this mass and velocity, like this. Now to infer values of some target variable given the observed values of other variables, right? Given that we are dealing with random variable, it will not generally be correct to assign the target variable a single determined value. Since we are looking into dealing with a random variable, that is why Bayesian belief network we say. So we don't think every time it will be correct. So we try to associate the probability distribution. So probability we try to associate and look whether it is true or whether it is false, and then we try to calculate. So what we really wish to infer is that probability distribution for the target variable, which specifies the probability that it will take on each of the probable values given the observed values of other variable. Right? Now this inference step can be straightforward if values of all other variables in the network are known exactly. If you know all the other variables, then this method you can apply. Right? These are some of the important points what you can make with our Bayesian network. If you know the probabilities of all these things like what is given in the table, then only you can calculate the joint probable distribution. Now otherwise, now it is very difficult to identify the joint probable distribution for this particular or by using Bayesian network, right? So now let us look into the some other concepts here. Okay, so you can find the difference between AV bias classifier and Bayesian belief network also. So as given in the notes, you can just later look into that. Basically, the main thing here is conditional, independency and dependency, right? So we are going to calculate the joint probability distribution also depending upon some set of variables, and we have seen that when we are considering some of the examples, so actually we wish to conclude the probability distribution for a target variable, and when you are going for it to calculate the target variable, so some set may be conditionally independent and some may be conditionally dependent. So until and unless we have all the probabilities are given, then only we will be able to identify or calculate the probability of a target variable in the Bayesian belief network. So here what happens is that the network structure might be given in advance or can be taken out from a training data set. Already the network structure will be given, or with our training data set you have to draw a network structure, and all the network variable may be directly observable in each training example, or some might be unobservable. As I told that, so some variables may be directly, it is visible for us, you can observe, whereas some may not be observable. In both the, if the above two cases are satisfied, then the learning the conditional probability table is straightforward, right? So then we can come with a conditionally probability table. So with that help of that particular table, now we can try to find the target variable. Now say this is another simple example is there. Now say it's very simple. Now you say that there is a rain, right? If rain comes or if rain is there, so the dog is going to bark, right? So if dog barks, then the cat will hide. Cat will go and hide. So there is a chance that you have got a cat. So sometimes, see, if the rain is very heavy, if rain is coming, the dog will bark. And if dog barks, cat is going to hide, right? So now, so if you are going to represent these variables as R and B, now there is, we are given a conditional table for barking of the dog barking, right? So dog is going to bark given the rain, the probability of this X given P. So now we can see here bark, right, and rain. So rain may come or negation rain. Rain is true or it is not true. So how many times when rain comes, dog is going to bark? See, sometimes when there is no rain also, dog is going to bark. If rain comes also, dog is going to bark. Now that probability, like say for example, 9 times you have calculated, you have a data set of 48. Out of 48 times, when you have recorded the entire data sample, when you have in this 48 data samples, when actually the rain is coming 9 times, it is true, and at that time dog is barking. And 18 times rain is not coming, there is no rain, 18 times dog has barked. Now similarly, now dog is not barking 3 times when actually rain comes, and 18 times it is not barking when even though there is no rain. This is the joint conditional probability table for this particular node dog barks. Now similarly for cat hides also you will be having another one table. So like this, when you consider the Bayesian network, for each and every nodes except the root node, you will be having the joint probability table. With that particular table, it becomes easy for us to calculate the target variable. So in the notes here, now you can see one simple example which is been given. So say calculate the probability that alarm has sounded, but there is neither a burglar nor a earthquake occurred, and David and Sophia both called the Harry. Now this is a scenario, it is like a story. Now what the story is that, say there is a Harry. Now he has installed a alarm system in his home, right? How this alarm system work is, when there is a slight earthquake, the alarm will ring. When there is a robbery also, alarm will ring, right? Now Harry has gone to office. Now there are two neighbors. So one is David and the other one is Sophia. And he has told both of these neighbors that if the alarm rings in my home, please make a call. And there is some conditions, right? Now this David, now he is little bit he cannot identify the difference between the phone ringing and the alarm ringing. Many a times it happens that even though phone rings, he thinks alarm is ringing and he may call Harry, right? Now what is the another neighbor? This Sophia. Now she is having another condition, another problem. What is that? She is always fond of music. She puts music systems in her home such loud that many of the times when the alarm rings also she cannot listen, or sometimes she cannot make the call. So this is the scenario. Now in this scenario, now you can see we have drawn a Bayesian belief network, and for all the nodes the table is given. So burglar, so whether the robbery is happening, true or false, what is the probability that robbery can happen, what is the probability that robbery cannot happen. Similarly earthquake, what is the probability earthquake will happen, what is the probability earthquake is not happening, right? Now when you take this alarm, now two things are there. So when there is a robbery and when there is an alarm, BE, what is the probability that alarm is going to ring when A equal to true? What is the probability that alarm is not going to ring when both are true? Right? We have the robbery or the burglary and the earthquake. Now there are two variables. So we have four possibilities. True, TF, FT, FF. And what is the target? Alarm may ring. A equal to true, A equal to false. Alarm may not ring. So the probabilities are given. Now similarly for David, again probability is given. So this David, again it depends on the alarm, right? So alarm can ring true or alarm may not ring false. And now David, probability of David equal to true. David equal to true means when he is going to make a call, right? And David equal to false means he is not going to make a call to Harry. So like this, the probability tables are been given. Now what you have to do, calculate the probability that alarm has sounded. So we will write the formula for joint distribution. So we will say probability of S. S is what Sophia calls, right? So you read the problem carefully. Calculate the probability that alarm has sounded, but there is neither a robbery nor an earthquake occurred. Neither robbery has occurred, earthquake is not there, but alarm has sounded. Since alarm has sounded, David and Sophia both call Harry. See, this is a chance where alarm has ring, David also makes a call to Harry, Sophia also makes a call to Harry, but actually nothing has happened. So you have to calculate what is the probability in this scenario. When there is neither a robbery has happened Neither an earthquake has happened, but both the neighbors have called the Harry saying that alarm is ringing. So we say probability of yes. What is this yes here? Sophia. We represent this as yes. So probability of yes. Yes, because Sophia is calling. D, David is calling. Both David and Sophia both makes a call to Harry. So probability of yes, comma D, comma A. So what is A here? Alarm is ringing, right? That alarm has sounded. So A, comma negation B. Why negation B? B is the burglary, that is robbery, right? So it has not happened. It is given here neither a burglary, so negation B, nor an earthquake, negation E. You have to find the joint probability. So now this will be equal to, now how we can write probability of yes given A, alarm is ringing and Sophia is calling, multiplied with probability of D given A, David is calling when an alarm is ringing, right? Multiplied with probability of A. So now here, see here 2, right? Now when you go for alarm, there are two possibilities, B and E, earthquake and robbery. So probability of alarm ringing given negation B and negation E, right? Multiplied with probability of this. See, both are conditionally independent. So when there are this and this are independent, so we are going to multiply probability of negation B into probability of negation E. Now this equation RHS, now everything is there in our table. So probability of yes, Sophia is going to make a call when alarm is ringing. Go to this particular table. So probability of alarm ringing, so yes is equal to true, right? So alarm ringing is A and Sophia is making a call, true. So what is that value? 0.75. So 0.75 multiplied with probability of D given A. So David is making a call, right? David is making a call. So true. True. You have to look into this row, this column. David is making a call. Given A, that means alarm is ringing. Alarm is ringing means true. So 0.91. Clear? Like this, you can look each values from this particular table and finally you can calculate what is the probability in this case. So this is a simple example now how we are going to use Bayesian belief network, right? So this is another simple concept of the Bayesian belief network. So next we have another concept called as the EM algorithm or expectation maximum algorithm. So that expectation maximum algorithm, so we will be discussing in our next talk. Okay, clearly study, understand Bayesian belief network. Thank you.